Okay, so what we can do is we can save variables from our program into files. So you see on the left here, and maybe I'll just get rid of my face so that you can see everything. Um, we've got our workspace on the right, and when you first open MATLAB, this will all be empty, clear all. Okay, but as you create variables like high score equals, I don't know, something large, you see that that's now a value that's in the workspace. Let me bring this up here. You can save out values into mat files. So you can say save, and then the value high score, right? So let me just show you. So help save. So for any of these commands, if you want to know more about them, you can say help, and then it'll tell you all this information. If you'd like to stay within the text workspace here, you can just type the word help. If you like to see kind of a graphic interface pop up like a web browser, you can say doc, that same command. But here is the way you use the command save, and then you give it a file name. Okay, and then that will store everything in your workspace. That might be more than you want, so what you can also do is say save file name comma variables, and only stores the specified variables. All right. Now the only trick here is that we're going to specify variables as a string. So let me show you how that works. So for example, we want to save this high score, right? Game data.mat, and then we would say high underscore score like this. And now in my left panel here, the files, you'll see this game data.mat file, right? So that game data.mat has my information, and if I load that file, then you see the high score pop back up. Okay? And so what you could do in your game is at the beginning, now you're going to have to create this game data.mat outside of your game, but right at the top you could say load game data.mat. And then at the end of your game, maybe if they got a high score or something like that, you could update that file, say high score equals 100,000, and then save it back out. That way the next time you run the game, even if you close out MATLAB, you would be able to get that high score back. Okay? What do we think? Does that answer the question? Okay. So the next thing I want to talk about, I think of general interest, is displaying something like a score in the game. So here we said message.string, and that is equal to a specific line of text, but that we can't change that, right? Everywhere we've used this technique, we've used a fixed chunk of text. So if you wanted it to actually be the current score, we need to use a different function. So for example, if we want to update our game so that we keep track of a score variable here, we'll set the score equal to 0. And maybe every time they pass an asteroid, they get a point. So every time one of the rocks falls off the screen, we add something to the score. Score equals score plus 1. Okay? Now I want to display the score to the user. I could just say fprintf your score is like that, and then score, but that would display in the command window, and the user would have to kind of have this split vision where they're looking at the game in one eyeball and looking at the command window in the other eyeball, and we wouldn't like that, right? We want to display that text in the game somehow. So this F in front of print, so printf is print a formatted string. That's what we want to do. We want to take some information here and dynamically, create this string. So that's printf. The extra f in front of here indicates we're printing to a file, and the file here is actually the screen command window. But what I want to do is actually create a new string with this so that I can then set the string parameter of my message. So here we've got, let's see, message.string, right? I've got to set this to a particular string rather than you lose, right? What am I going to put here? So I'm going to say message string equals s printf. So this different function is going to return back a structured the result in a string, and so then I can set that equal to message string. So you're going to use sprintf and capture the result in a variable, and then set the string parameter of your text to that piece. Now you can do all this in one fell swoop by just setting the .string to here, but I wanted to kind of show you explicitly what's happening, right? So here it's all one go, right? We're calling sprintf, and the result of that is getting set to the string. See, my MATLAB is busy crashing right now. Oh, all right. Well, there goes MATLAB, but hopefully we can bring it back. Sorry, you're not the only ones with technical difficulties today. You can enjoy some Python code while you wait. Let's see. All right, one moment. Okay. Perhaps now. So now I'll try to run my game. Let me dock it so that you can see what I see. And now you see my score is incrementing as I go through. Okay? All right, so those are the topics I think are of general interest. Did anything else come up while I was going over those that makes you think, yes, that's what I want to know about, or any other topics? Let's see. Andrew said, "What's it for?" The code. Did it? Oh, that's for the senior elective in 4:30. So in that game, we're actually making a video game as well. We're making Battleship. So every week they do a new portion of that code. Good question. So. All right, then let me create a breakout room, and then in the chat, let me know if you. I'll talk about gravity first, and so if you're interested in that, put something like in the chat to indicate your interest, and then I'll put you in that breakout room. And the rest of you will go in a different room and can chat amongst each other themselves. Like you're gonna be lonely. Nobody else wants to know how to implement. Oh, we got okay. The in-person class wants to do gravity. Okay, well that'll be good. Yeah. Okay. So projectile motion, the same thing. Yeah. Although then you'll have to know tracking as well. So maybe you can stay in both. Okay. Great. So let me create the breakout rooms here. Two rooms, manually assign people. Okay. And so we want in person, Zach White, Ben Watson, Daniel, and Zach Tiang. Okay. Zach, Ben, Daniel. Okay. All right. Great. So everybody in here wanted to learn about gravity, right? Okay. Good, good. Okay, so let's well, first I'll tell you how it's done, and then maybe we'll try to implement it in asteroids by using gravity to actually pull these things down rather than having them fall independently as they do right now. So gravity is a force, and it affects motion through the acceleration of that body, right? So F equals ma is that great relationship that we know of from physics. And so what we really want to do is to, in every frame of our program, we're going to update the position of an object based on its velocity. And we've been doing that. That's how the rocks fall or the ship moves, right? We have a speed times a dt. But that speed now is going to change each frame as well. And it's going to change by the acceleration. Right? So if we want to know what the speed at time 2 is, and we know what the speed at time 1 is, what's the equation to find the speed at time 2? Let's put this back over here. Sorry. So, in going back to position, right, I guess to make it easier, right, if we say, and typically in physics we use x for position, so x at 1 equals, x, if this is going to be discrete time steps, which it is in our game, because we're doing frame by frame, x at 0 plus the velocity times dt, because this is the change in position, delta x. Right? We'll do the same thing for velocity, though. We'll say that my velocity at time 1 is equal to the velocity at time 0 plus acceleration times dt, because this is my delta v term. Okay? So what we're going to do is simply add a line of code to change the rock speeds each time. Right now those are constant, and they don't change. So let's try to update our game so that the rocks actually fall due to a gravitational force. Okay? So maybe we'll start the rock speeds at 0. So we have 4 rocks, 4 zeros up here. Okay, and if I were to play this game now, nothing happens, right? Because every time in the main loop here, I say move y by, and what am I moving it by? -1 times 0. Okay? So what you'd want to do in here would be to say step 0, apply physics. And to do that, you're going to update the velocities. Okay, so... And I'm writing it like this because you might have other things you need to do to update your physics as well. So you could do it in the move rocks around loop, but let me just split it apart so it's clear what we've added. 4 equals 1 to length rock speeds, and we could say length rocks, they're the same length, so it doesn't matter, but we could say here that rock speeds I is equal to rock speeds I. And now what are we going to do? Add or subtract from the speed? Well, now here we've kind of fudged already with our signs. We're saying, well, they're going to be moving down. Now with our game, we'll keep a strict relationship that the rock speeds and already has the direction built in here, and that our force, our force due to gravity, is in the down in the y direction. Okay, and so that will only affect the rock speeds in the y direction. The x's won't change. And then here I'd say gravity times rock speeds. Okay, and then way at the top here, I define gravity, and this would be a tunable knob, right? And so gravity on Earth is the acceleration due to gravity, that is, would be like, just like here, like these are my knobs, right? Gravity equals negative 9.8 if I'm on Earth, but you might find that in your game that's too fast or it's too slow, so you could just play with this number, but it should be negative, otherwise they're going to go up. So now let's see what happens. What have we done here? Oh, not equals. Sorry. Rock speeds equals rock speeds plus, and then this delta term here. Sorry, for somehow my font my screen continues to get smaller and smaller, the viewable area that you can see. So I'm sorry I have to do all these crazy indents, but you can certainly fit it all in one line. You're going to update each speed by, if I could even type, setting equal to itself plus a delta value. I think my cold is affecting my brain. The delta value is a meters per second squared. So multiplying that by seconds gives you a meters per second. And so, of course, you can then add that to another unit that is also meters per second. And you see the physics works out. I'm sorry for the numerous typos there. But this now should give me the behavior that I want. Now, be careful. With gravity, the velocities are going to continue to increase. Okay, so now let me run it so I don't die the first time through. But notice how they're getting faster. If that's not dramatic enough for you, you can certainly dial up gravity. Say it's now negative 10. But see how they're getting faster and faster? That might all of a sudden be way too fast, so you can set it so that the velocity resets to 0 at some point or something like that. But that will give you a gravity term. And if you follow, I'll go back and I'll stop this and do a tracking one. But you can use this to get a parabolic trajectory kind of for free. Right, so if you gave a rock some initial vertical component, so it was actually going upwards, and then gravity would slow that upward movement and eventually reverse it. Okay, and if you then also were translating it at x at the same time, moving it toward across the side, you would see it traverse a parabola. Okay, so gravity by itself is pretty straightforward as long as you don't make the typos I initially did there. What you're going to be doing is changing your velocity incrementally every time you have a frame. And so you're going to take a meters per second squared term times dt to get meters per second, and then use that to update your velocity. Okay. Other caveats, right? You need to fudge it if you're moving the rocks around and you don't want them to fall at the bottom of the screen, then you would say, hey, if your y by is below the screen, then you've hit the earth, right? Even though gravity's still acting and your velocity should still be pulling you down, you can't go further. I'm just not going to move you further down than what I think the ground should be. Does this give you enough information to go forward? Okay. Any questions? All right, great. So I'll end this breakout room and then we'll go to the tracking. And I'm recording this whole thing, so if you don't see one and you wanted to go back and look at it, you can go to the class recording and see both of these sessions. But that way, if you want to work on your own, I'm not talking in your ear. All right, so I think you're all back now. If you'd like to talk about tracking, go ahead and indicate your desire to do so in the chat, and then we'll break that out. And I mentioned to those that were in the gravity, if you decide later on you want to learn about this, I'm recording this all in the same screencast, so you can come back to this anytime and watch the video. All right, some of you doing both here, doing some elaborate games. Oh my, good. You don't know what you're in for here. Tracking is a bit tricky. But, okay, so not the in-person classroom then. Okay, so Ben Watson. Daniel. You mind tracking. Okay, fair enough. Connor. Oh, Zach White as well. Okay. Okay, great. Okay, so, and this is the tracking crew, right? We all went tracking here? Okay, good. Some of you guys seen before in a previous room. So, tracking is going to be a bit tricky because what we've done so far is separate our movements in X and Y and dealt with them each individually. Now we're going to have to consider an object's velocity independent of its direction. Like the ship might be moving at 3 units per second, but is it moving in Y or in X or in some combination of X and Y? Okay, so let's draw it out and see if we can figure out the math we'll need. So imagine you want like a black hole in the center of your game board, okay? Well, a magenta hole, I suppose. And your goal is to have all of the objects kind of get pulled into this hole. And I guess here we'll talk about gravity too, but I think most of you were in both, so so there you go. Well, we don't have to combine the two concepts. Now this is x, so we have a move x by, and we have a move y by. But what we really want to do is move in some other direction that's kind of mostly x, but some y. Okay? And presumably all these objects are going to have a speed already. Like I said, going to be moving at 3 units per second, just to make up a number. And so the rate at which they move should be independent of the direction they're moving, right? They're either moving 3 units this way, or they're moving 3 units per second this way. Let's not have that be a triangle. Or maybe it's 3 units per second this way, right? This is actually, if we drew out all the potential movements here, the shape of this would actually be a circle. Right? Because they're all vectors of the same length, and every possible position here, they're going to swipe out a circle. Okay? So let me zoom in, I guess, into this little wedge I've drawn. So here, let's look at this closer. And I'd like to decompose this blue vector that's kind of pointing in a little bit x and a little bit y into an amount in x and an amount in y. Because once I do that, I can say move x by a certain amount and move y by a certain amount, and I'll get the effective result. Okay, so this is my x direction, this is my y direction, and here's my desired velocity. My effective velocity is in this direction here. Okay? So what two vectors sum up to produce this result? Well, I could move my object over here first and move x by, and then move y by up to here, and a two-step process, and I'd get to the point I want, right? Well, how much do I need to walk in each direction? I need to figure out the distance of each of these legs. I know this value. This value, we'll call it 3, just to keep up with the model we've been talking about. So if I know this is the hypotenuse of a triangle, and let's say I also know this angle theta here, I'll be able to find that angle theta by comparing the position of the orange square to the magenta blob. That angle here is the center point of this square to the orange blob, right? Or to the black hole. Okay? We'll have to do the math to figure out what that angle is, but assume that for now we know it's a theta. So what's the math that I need to apply here in order to find the unknown x and the unknown y? And this is actually a question, so I don't know. Daniel, what do you think? Sometimes I just ask myself and then answer, but I should stop that.
Are you asking like how to find the x and y vectors of that?
Right, yeah.
So you'd take like the sine and cosine of theta?
Perfect, right? We know the relationship SOHCAHTOA, right? That sine of the angle theta is equal to the opposite edge, in this case y, over the hypotenuse, which in this case is 3. Cosine of theta is equal to the adjacent edge, in this case we're calling that x, and over the hypotenuse, which in this case is 3. And we don't need the tangent relationship yet. We'll find that we'll need that to actually calculate theta in the first place. But right here, we'll just use a simple bit of algebra. We'll multiply over by the hypotenuse, and so my effective x is equal to the velocity vector. Sorry. Which is going to be 3 times the cosine of the angle, and y is going to be equal to 3 times the sine of that angle. And we can just check our math here with our intuition. If I am moving horizontally, that theta is going to be equal to what, Ben Watson? If you're moving directly horizontally, what would theta be?
0.
0. And cosine of 0 is
1.
1. Good. And sine of 0 is 0. And so yes, you're moving 3 in the x direction. And you should check, again, when you're moving vertically, that's an angle pi over 2, or 90, however you want to think about it. And at that point, cosine is 0 and sine is 1. And when you're in between them, you're split, right? You have equal components x and y. But they're not equal to 1.5, right? Okay. So that's, if you knew the angle already, that's how you would split an x speed. If you knew that it's for example, your game was like a shooting game, right? Where like Angry Birds, where you've got a a cannon here that the user sets up, and they basically dial in theta, right? They set a desired theta. Okay, and then they'll also set, say, a desired velocity. And then you want to launch an Angry Bird that has a certain amount of x speed and a certain amount of y speed. Okay? So the question is, given v and theta, can you give me vx and vy? And the answer is yes, you can. Vy is equal to v times sine theta. And Vx is V times cosine of theta. All right? So maybe at this point you're thinking to yourself, I have a different game I'm thinking about now. But it's not too bad. We just need to have two pieces of velocity and deal with them separately. Okay? Now, if you followed both of these together, if you wanted if you shot it this way, your Angry Bird would go into space eventually, right? Your Angry Bird would follow this path. And if we want the Angry Bird to fall, we need to apply gravity. And so what we would do in that case, initially when you fired it, you would set y speed equal to v sine theta x speed, right? But then every time through the loop we apply physics, we would subtract a bit off of which one? The x or the y? Maybe Zach White. We can both, I can't remember.
Oh, y?
The y, right? We leave the x alone. The x is considered orthogonal, right? It's at 90 degrees to the force, so it doesn't see the force at all, right? X is unchanged. But y, you're going to start to lose some of that y velocity. And so you initially start going up quite quickly, and then you start going slower and slower and slower and slower until you stop. Your velocity actually comes to a standstill, and that's at your apogee, at your peak. And then that velocity keeps getting subtracted from. Every time through the loop, you're subtracting a little bit off the velocity, and so you start dropping faster and faster and faster. And that's actually what traces out a parabola. All right, so the parabola will evolve naturally just based on your use of the right relationships. Okay, and that would be if you subtracted off a gravity term each time through the loop. Okay? So, the theme here is that there's nothing secret or, clever in terms of MATLAB to implement these features. It's just more algorithmic thinking. Like, okay, I know physics. How do I apply that knowledge into a programming environment? Oh, I need a for loop for this. I need to do some trig, right? It's all there for you, but sometimes unpacking and figuring out how to use it is a little bit tricky. Okay? So that is, I would say, maybe level 1 tracking, saying, hey, I was given theta, like someone specified this, or it's fixed ahead of time and I know what it is. A harder problem would be going back to our original page, saying, well, how do I get that theta given two objects in space? If I want one object to go towards another object. Okay? So we can talk about that next. If you'd like to stick around and hear that story, you can stay here. But I also think you should have the ability to leave these breakout rooms. So feel free to pop out if you want to just work by yourself. Okay? But for those brave souls that want to continue forward, let's talk about how do you find this theta. Okay, so to recreate the story from that first slide, but it got a little bit busy, so I don't want to continue editing it. I have my two objects here. And I can find a point that represents the center of each object by doing the mean of the x data and the mean of the y data. So I can get a point, a single point that represents each object. Okay? Now, what I want to do is figure out the right triangle that describes their relationship. Okay? So this is going to be some delta x and some delta y. And I'm going to find these by subtracting the y, this is x 1, y1. Oh, I should write y1 here. And this is x2, y2. Okay, then delta y is equal to y1 minus y2. And of course you got y1 because y1 is equal to the mean of object dot y data. Okay, and delta x similarly is x1 minus x2. And this might be negative, right? In this case, you're going towards the left here. So this, in this case, is a negative value. Now, if I know the sides here, the last trig relationship, which we didn't use previously, was tangent, was TOA, right? Tangent tells me a relationship between the opposite and adjacent sides of a right triangle. In this case, delta y, which is the opposite, over the adjacent, which is delta x. Now I know delta y and delta x, but I don't know theta, and so I'll solve for theta by taking the arctangent. So theta is equal to arctangent of delta y, delta x. Okay? And that's how you would then get your theta to go apply the math to break velocity into an x and y components. Okay? Now, the only caveat here is that there is some ambiguity in the sign. So there are four possibilities here. Okay? The theta here, you could be pointing in the upper quadrant this way. You could also want to be pointing over this way, so having some negative x velocity, but also positive y velocity, right down here. So you have four quadrants, and where you could be moving, right? And there's only two possible signs for the inside of this equation here. This can either be a positive or a negative number, right? But there are four different results that I want to get out of here, four different thetas. Okay, so the problem is that a negative over a positive looks the same as a positive over a negative, but they correspond to different quadrants in the graph. So MATLAB has a function atan2, which will do the right thing. So you could just say atan in MATLAB, and give it a single value, and it will give you something in the right half plane. But if you want a 4-quadrant inverse tangent, which you do in this case, you'd want a tan 2, and then you'd pass in the components separately, and then it can figure out the positive negative relationships and give you the right result. Okay, so what I'd recommend is starting to write your game and then carefully stepping through the code once you've written it, and to figure out these different angles and use print statements and pause the execution. I don't think it's that helpful for me to go through a knockdown drag out implementation of this, because it's probably not exactly what you'd want anyway. If you do have your code tweaked up and there's just a glitch in it, I'm happy to look at your specific code, but hopefully this gives you a path forward, at least, or again, a way to say, you know what, maybe I don't need to do tracking. But there you go. Any questions? It looks like my in-person class is heading out. Are they done? Oh, you know what? I was thinking today was a lab day. All right, sorry. My fault. You are all free to go here. And we will talk again in lab tomorrow. All right.
Hey, sir. Can I ask a quick question about how you want us to turn in lab 3?
Sure. Let me end these breakout rooms and tell these other poor folks that... Hey, sorry. All right. Yeah, and I guess everyone's... Okay, you're probably in. You're free to go. Sorry, I had mistaken the 2 days. We have a lab tomorrow, and then I'll have my 2 hours for you. So, Ben, you stick around. But Zach, you have a question?
Yes, sir. So I submitted something. It was just the script of the code for section 4. But I guess somebody else mentioned that we should be using the publish function or something like that.
Yeah.
So how exactly do you want us to turn it in?
So ideally what you could do, and let me go back to MATLAB here. No, actually stop the recording.